So today I will discuss one of the very simple concept of third semester, and course is 15 and unit number 1, and that is acid base catalysis. Actually it is a very very old concept, and according to your course content you have to study complete acid base catalysis. And actually the acid base catalysis can be divided into two parts. One part is specific acid base catalysis and another part is general acid base catalysis. And in addition to some fundamental knowledge, you have to learn one of the most important aspects of the acid base catalysis, that is called pH rate constant profile. That means, suppose you are doing some experiment. Say for example, I can give one example, that is called the muta rotation of glucose or enolization of the ketone. So with the help of this concept, pH and rate acidity constant profile, you are able to identify, suppose you are working in the presence of hydrogen ion as well as the hydroxyl ion, but you can calculate the minimum concentration of hydrogen or hydroxyl ion, so that, because this reaction is responsible for hydrogen ion as well as the hydroxyl ion, but if you understand that equation, then you can say yes, this is the minimum concentration of the hydrogen ion where hydrogen ion catalysis is predominating and hydroxyl ion catalysis is unimportant. Now as you know that if I ask you that what is the definition of general acid and general base catalysis and specific acid and specific base catalysis. Now definition is very simple, as name itself is a definition. If it is a specific acid base catalysis, that means only hydrogen ion and hydroxyl ions are responsible for catalysis. So therefore it is called the specific acid base catalysis. That can be divided into two parts, specific acid as well as the specific base. And it was discovered long back, I think Oswald, Arrhenius, like Berzelius. But after the discovery of Bronsted-Lowry concept, it was observed that not only hydrogen and hydroxyl ion are responsible for catalysis, but some other Bronsted acid and Bronsted base. So for example, sometimes what happened, some cations of very weak bases like NH4 ion or anions of very weak acid like acetate ion are also responsible for catalysis. So that type of catalysis is known as general acid base catalysis. But fortunately, if you understand one type of catalysis, you can write rate laws for all these catalysis. And I have already told you that today I will also discuss not only the acid base catalysis but also pH rate constant profile. And what is the meaning of pH rate constant profile? That means if we plot a graph between log of K observed and pH, you will get different types of graphs, different types of lines. And on the basis of these lines, you have to predict the nature of the catalysis. And that is a very important question for the examination. And as I have already discussed with you, that the specific acid and specific base catalysis is a very old concept, whereas this general acid and general base catalysis and this pH rate constant profile is not very old, because it was developed by Dawson and Poise in the year of 1930. Now, just I'll discuss how you write the rate laws for the specific acid base catalysis and general acid base catalysis. So I will explain gradually, but this is a very important plots, and you see, you have to identify the types of the reaction, and you have to explain the behavior of different types of profile. And I have taken this pH rate constant profile from a very important book, The Physical Basis of Organic Chemistry by Howard Maskell. And this type of plots or profiles are also available in chemical kinetics by K.J. Ledler or Lowry and Richardson. It's a very important question for examination point of view, that we suppose you are doing some experiment and you are getting such type of plot. Sometimes slope value is positive, sometimes slope value is negative, sometimes there is a flat region, sometimes there is no flat. So how you explain this behavior? That is the beauty of this pH rate constant profile. Now, as you know that because we are dealing with the physical chemistry of the acid base catalysis, but it is my advice to the student that you must also learn or collect at least 2 examples of each of the system. That means there are 4 systems: specific acid, specific base, general acid, general base. So you must know 2 examples of specific acid catalysis, 2 examples of specific base catalysis, 2 examples of general acid, and 2 examples of general base. I am giving some of the very simple example of B.Sc level. Everybody is well aware of this reaction, because during your M.Sc first semester practical, most of the students have done these 2 experiments. One is acid catalyzed hydrolysis of the methyl acetate, and second is the saponification of ethyl acetate. I am not going into details about the mechanism of all those reactions, but I am just giving you the reaction where hydrogen ion is only responsible for this reaction. So therefore it is called the specific acid catalysis reaction. Whereas saponification of ethyl acetate, here hydroxyl ion is responsible for this catalysis reaction. So therefore it is example of specific base catalysis reaction. But you must know the rate law of specific acid and base catalysis. So if it is a specific acid and base catalysis, hydrogen ion as well as the hydroxyl ions are responsible. Now I am coming to the general acid. When I discussed in my last class regarding the Bronsted catalysis law, and one of the most important example of ethyl vinyl ketone hydrolysis. Ethyl vinyl ketone hydrolysis. That is also example of general acid catalysis, because here hydrogen ion as well as some undissociated weak acid like acetic acid, formic acid, chloroacetic acid, cyanoacetic acid are also responsible for catalysis. So therefore it is an example of general acid catalysis. Now in this enolization of ketone is also an example of general acid catalysis reaction. Here is also you see that first part is the protonation of the acetone and then the attack of water as well as this weak acid. So it is also an example of general acid catalysis reaction. But of course, sometimes what happens, we can write it is an example of general acid base catalysis. The very simplest example of general base catalysis reaction is the aldol condensation. You all know this type of the two equivalents of the aldehyde form. So it is an example of aldol condensation is an example of the general base catalysis reactions. Now I am coming to this. Listen very carefully. It is a very simple thing. If you understand, it is a common for acid base catalysis. Now if you understand this simple reaction, you can write any reactions. Android, which is Android? Okay. Right. So let me start with here. Acid base catalysis. Okay. So it is first divided into two parts. Specific and general. Specific, again two parts. Specific acid, specific base. General acid, general base. Now if you mix general acid base, if you add this specific acid. So now only hydrogen ion, only hydroxyl ion. But if it is a general acid, hydrogen ion as well as general acid is also responsible. Hydrogen ion as well as general acid. And if it is a general base, hydroxyl ion as well as the general base. You follow my point? Now we have to solve all one by one. Then, now what is the specific acid base catalysis? So it will hydrogen ion as well as the hydroxyl ion. And if it is a general acid base catalysis, a big equation. Hydrogen ion hydroxyl ion, undissociated acid, as well as B. So if you see the leader book, the rate law is like very big. But if you understand, it will be very, very easy. And like acetate ion, as I told you, that anions of weak acid, as well as the cations of very weak acid, they are also responsible for this. So this is the classification. Now I am coming to general. If you understand one system, you can solve any equation. That is the beauty of these things. So let me start with normal cases. It is for all. It is for all. So A is converted into B. Again, I am very simple. No catalyst. No catalyst. No catalyst. So it is rate is equal to K0 and A. This is first order rate constant for uncatalyzed reactions. Second reactions. A is converted into B. There is a catalyst C. So rate is equal to, depends upon the K0A plus Kc, second order catalytic constant. A C. Sorry. You follow this point? So generally what we do, generally K observed is equal to A. So therefore K observed is equal to K0 A. This is the final equation. That means if we plot a graph between K observed and catalyst or straight line or whatever it is dotted. So now if you understand these things, you can solve any type of catalysis. Now this is common for acid base general catalysis. Now suppose you will write same thing for specific acid. If you understand this thing, anything can be. A specific acid, I am taking a ester. My system is hydrogen ion and it is formed product or whatever it is, then production. So same thing I will write. First is rate is equal to K0 E. E means first substance. There is a possibility. Suppose there is no catalysis, but in spite of that there is a possibility. It's okay. Then you add hydrogen ion. So again K. Now I am write hydrogen plus. I am write hydrogen plus. Where Kc. But now we know the catalyst. It depends upon the E plus E and E. And I first write, suppose K0 E. So total rate K observed T. So nothing new. K observed is equal to K0 plus K8 I'm sorry, I must write here or H or H3O you can write. So K and 8 plus. So is there any difference? Nothing. 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 Now I would like to write for specific base. Now I will write for specific base. So what I do? That's very simple. So suppose there is no catalyst. Now catalyst K observed D, K0. Very simple, it is just 2-minute job. Okay. Now last part, that objective type question can be asked, what would be the final equation of specific acid base catalysis. So I should write in top. K observed is equal to K observed is equal to K0. Now I am writing, first I have written specific acid, then specific base, now complete reaction for specific acid base catalysis. So K0, K8, 8 plus or H3O you can write, plus it's very simple. Now I will write general acid first and then general base. Then we will mix it. That part will be, so you see, so simple. So I think that will be much better system. That board. Now I am writing general acid. All are available in this book. General acid. So A is converted into B. If it is a general acid, it depends upon the hydrogen ion as well as H. If it is a general base, B, hydroxyl ion and the general base. So same thing you will write, that rate is equal to first, you have to write first thing, K0A. I am writing only one. I will not write the general base and like that. Then it also depends upon the K0A plus KH A plus K A, it is also second order. H and A. You can write ester, acetone, any type of things. So K observed is equal to K0 plus KH or H or hydronium ion you can also write like same thing. K H H. In some books it is utilized as a summation, that means all the ions dissociated or undissociated part is also. So summation of this OH. So same thing if I want to write for general base. So K observed is equal to K0. I am writing now general base. K OH, OH negative, KB and B. Finally, I am just coming to the last part of this equation. So this is for specific acid-base catalysis. Now I will write general acid-base catalysis. So I will sum both the things. So it will be big, very big equation. Again, it is for objective type question. So K observed is equal to first K0, KH, you see here. H or hydronium ion you can write, no problem. So it is a very big equation. K, H, H plus KOH. Just practice, as I always told, the practice makes a man perfect. It is so simple. Sometimes, as I told you, you can. So this is the complete equation of this general acid-base catalysis thing. So now the last part is that which should be the minimum hydrogen ion concentration or maximum hydroxyl ion concentration. So that equation is very important. That is called the pH rate constant acidity profile. Okay, it's clear? So same thing I have just explained here. That means if you understand this equation, it's a mechanism, and it will take only 2 minutes, 5 minutes to understand. That means same thing, catalyst, any type of catalyst, acid, base, general base, and always remember that if there is a catalyst, always it is second order catalytic constant, and finally we will get this type of things. Now my question is that suppose we have studied, we understand all these things, but we get different types of plot. Again, this is I am taken from, you know that edition is very important. Edition of the book is very important. Edition. You see, this is the third edition. This is third edition. And this is second edition. And it is, I think, 1983 or like that. I am just giving two plots. Both are from, I am taken from the Ledler. But one is third edition and this is the second edition. And you see the explanation process, this plot is very easy to understand, whereas same, both are Ladler, only third edition, that is always there is an improvement. First thing that this type of plot is there. Same reaction, but the presentation is different, and this is the new type of plot. So now how do you explain all this type of the behavior? Let me explain these things. Okay, suppose now I am coming to last part, pH, rate constant, profile. Very important. Why? We know that for specific acid base catalysis, so our reaction is like that, K0, K observed is equal to K0. Just listen very carefully, this is the last part. KH H plus or H3O, you can write H plus, no problem, plus KOH and OH. Okay. Suppose you are doing a reaction where pH is less than 7. So what happened, that the value of KH better than KO, and you are doing pH that case also and it is uncatalyzed part. You cannot predict these things. It depends upon the nature. So if I take a log and we assume that this uncatalyzed reaction is not very important, so I can write log of K observed is equal to log of K plus log of hydrogen and concentration. You know that negative logarithm of, so it is minus pH. So if I plot a graph between log of K observed and pH, and I am getting such type of plot where slope is negative, in first case, so we will assume that it is a specific hydrogen ion catalysis reaction. The hydroxyl ion concentration is unimportant. On the contrary, if I plot a graph between log of K observed and pH, maybe 1 to 7, 7 to 14, whatever it is, if I am getting such type of positive slope, then we can predict that this is a specific base catalyzed reaction. And suppose I am getting such type of plot, it indicates that the K0 uncatalyzed reaction is not there. But if I am getting red color, sorry, so that means there is a K0. Now I am just explaining this thing. See, there are sometimes what happens if you refer the good books like Ledler, they have given the name of the reactions, that in which case, in first case, suppose this type A, then there is a flat, then B. That means it is an example of muta rotation of the glucose, where yes, there is a possibility of acid catalyzed reaction, there is a possibility of base catalyzed reaction, and there is a possibility of uncatalyzed reaction also. So therefore there is a flat. But in some cases this is not visible, you will see. That means the possibility of uncatalyzed reaction not there. Somewhere there is a base catalysis type of the reaction, but up to certain pH there is a flat. That means it is a base catalysis reaction, but uncatalyzed reaction is also significant. Whereas in some cases acid catalyzed reaction is also there, but there is a possibility of uncatalyzed reaction. But question arises that you must know, you must calculate the maximum concentration of hydrogen ion or maximum concentration of hydroxyl ion, where you can say yes, this concentration is unimportant and this concentration is predominant. And that equation was developed by the Skarbel, a great scientist, and I will explain that Skarbel equation. Now, in new edition of the Ledler, they have very nicely explained all these things, that the slope value is 0 here and 1 to 7, same thing, but only the, you know that this is the representation style. This is the representation style. There is no difference between the old edition but the new edition, but they have mentioned all the such type of reaction, like which is the enolization of ketone, where is the aldol condensation, and like that. So therefore I just instructed you, I advise you that you must write at least 2 examples for each system. Sometimes in examination they may ask, write 1 example of general acid base catalysis reaction. Write the rate law for specific acid catalysis reaction. Or suppose there are 4 examples, you have to tick which one is suitable for general acid base reaction. So very simple. So the last part again, I am coming, last part. Clean all. No, I think I should not clean all this part. So good, no problem. Skarbel equation, it is called, sometimes it is called the Skarbel equation. But it is not so easy, because you know that sometimes what happens, because it is a very big unit. We have already studied the Bronsted catalysis, Bronsted acid law, acidity function, then linear free energy relationship. Then after this I will discuss the enzyme catalysis in next class. So, but otherwise sometimes what happens, if you see some old question paper, that sometimes there is a possibility of such type of question that they will give some example, suppose some reaction, and then you have to decide whether this is a general acid reaction or specific acid reaction. So that is also there, but I will not explain all these things. This last part is the Skarbel equation. That means maximum or minimum concentration of the hydrogen ion or hydroxyl ion. Suppose I am using in one case 0.1 N hydrochloric acid, and in one case 0.1 N or M sodium hydroxide. You have to decide it. So there are three parts: left hand side part, right hand side part, and there is the intermediate part. So how do you solve, how do you calculate this Skarbel equation? First thing is that I can do one thing, that I know that H2O is equal to hydrogen ion and hydroxyl ion, and Kw you all know. Kw is equal to water remain constant, and the value of Kw you all know, 1 into 10 to the power minus 14. So suppose it is up to you. You would like to eliminate this OH, or you can eliminate the hydrogen. Suppose in first case I will eliminate the OH. So I will write OH is equal to Kw divided by hydrogen. You follow my point? So K0, KH, 0.1, hydrogen ion I am taking suppose 0.1. So plus Kw is 1 into 10 to the power minus 14. Divided by 0.1, isn't it? So it is 10 to the power minus 14, 0.1 minus 13. So if I compare with 0.1 and this part, right hand side part, this part can be eliminated. So the predominating factor is hydrogen ion. Similarly, if you just remove the hydrogen ion, and here you will get same thing, 1 into 10 to the minus 14 divided by 0.1 sodium hydroxide. So this part will be eliminated. But our objective is that we have to calculate the minimum hydrogen ion concentration or hydroxyl ion concentration. So for that, again Kw is equal to H so OH is equal to Kw. So I should write here. Actually, the role of K observed, you can eliminate the role of K observed. So I can write KH hydrogen, because I consume that. Then KOH, Kw divided by. Now, according to Skarbel, in order to determine the minimum concentration of the hydrogen ion, so the left hand part should be equal to the right hand part. So I am just solving this Skarbel equation, that K H should be equal to K OH KW or KH square, you know, KOH KW. Therefore, hydrogen and M, minimum concentration, is equal to KOH KW divided by KH. Last, very important equation. Minimum is equal to under root of, there is some possibility of some numerical problems, but so this similarly we can also determine for the OH also, same thing. So this is called the Scarbell equation. That means, suppose again I am just doing so many times mutation of glucose or enolization of the ketone or vinyl methyl ketone ka hydrolysis. So that means in order to know that what should be the minimum concentration of the hydrogen ion, where this reaction is catalyzed by the hydrogen ion, whereas the hydroxyl ion is negligible. So that is the last important equation. So this is the final conclusion of this equation. So very briefly, I explained today the types of the catalysis, not of course acid-base catalysis. I must summarize. There are two types, specific and general. Specific acid, specific base, general acid, general base, and then ultimately we determine the actual concentration of hydrogen ion, or if you remove this hydrogen ion, you can calculate the OH ion. So that is the part of the very briefly acid-base catalysis reactions as per your course content. So in next class, the last part of this unit is the enzyme catalysis. So I will explain the competitive inhibition as well as the non-competitive inhibition. So thank you very much.